My name is Rob Alexander, and welcome to my talk on VPC design. This is the 4th year that we've been doing this talk. How many of you have seen this before or been to this one? Couple? Good, thank you. Appreciate you coming back. There is new stuff, don't worry. But we always start with this slide, and that's because this talk is based upon practical designs we see working out in the wild in production workloads with our customers. And we kind of distill those down every year and find kind of the best designs we see working, where customers are doing interesting things with VPC, and that's what this talk is all about. So do try these at home. There's nothing theoretical here. I will also point out that I do read all your feedback, and the overwhelming feedback last year was more designs, less screenshots of router configurations. So you'll notice we cranked down the level from 400 to 300. That is directly due to less screenshots of router configurations. So please give me feedback again. Let me know if I got the porridge right, and we'll correct for next year if I didn't get it quite right. So it's 300 level talk, but I don't spend a lot of time talking about the basics. So if you don't know what a route table is in VPC, you don't know the difference between a security group and an ACL, you don't know what direct connect is, you don't know what a NAT Gateway is or why you would want one, there's a few talks for you that you might want to watch in advance. So these two will give you a firm grounding. You can listen and hopefully get back and catch up on the things that you might not have caught the first time around. So when I first started this talk 4 years ago, it was mostly about why you would even want one of these things. Customers were like, why do I want to go into VPC? What is it good for? That has quickly changed. And these are more of my conversations today is how do I build something like this? So we are going to get to that, and that's what this talk is about. It's getting from one to this. But first you have to start with one. So a VPC, a virtual private cloud, is your isolated container, your own private network within AWS, where you define all the networking that goes into it. And upon creation, the one big decision you have to make is you have to choose what IP space to allocate to it, a CIDR block to designate for all the resources that you're going to launch in that VPC. So that CIDR's fixed on VPC creation, and you can't change it after you designate it. So the biggest is /16 all the way down to /28. And I always recommend go big. Go as big as you can. If there is not a reason for you not to go to /16, do /16. If you're worried about wasting IP space, don't. I've never had a customer come back to me and say, I wish I would have made that VPC smaller. The opposite, however, it happens way too much. So just a few guidelines on that IP space design. So a few recommendations. Clickers not behaving. So plan for expansion. If you're not going into, if you're only going into one region, think about other regions when you're thinking about your space and make sure it's still going to make sense with other regions in play. Absolutely consider future connectivity to your corporate networks, other partner networks, any kind of external connectivity you might be in. Have that in mind when you're designing your IP space, and make sure you're not overlapping. That's just asking for headache down the road that you don't need. So the next thing after the space, after the VPC space is you gotta carve out some subnets. So subnets are availability zone specific. VPC is a region-wide construct. Subnets are AZ specific. Make sure you distribute your IP space equally across all AZs. If you're in a region that has 3 or more AZs, make sure you plan for that. So even though you might only be going day 1 into 2 AZs, save that equal distribution of IP space for at least 3 AZs. I promise you, in a year or 2, you will want that space. Maybe even a few months, depending on how you go. Each AZ has its own resource pool. So for example, if you're in the spot market, that's a whole nother market over there that you're not taking advantage of in that 3rd AZ, so plan for it. So what about subnets? How big, how many should I have? Well, not this many. And again, this is not uncommon. I spent many years in enterprise IT, and we used subnets as a unit of deployment and a unit of isolation. This is very common. And the tools that you have available to you in VPC are much richer and much more, give you a lot more functionality than a subnet. So if you do this, if you do one subnet for application and across 3 AZs, you are going to have at least one person with their full-time job of managing your IP space. And it's just not necessary. So these are my recommendations for VPC subnet design. The first thing is that traditional switching limitations and the reason that you might have done that in your own data center don't apply here. There's a virtual network. There's no performance impact for having thousands and thousands and thousands of instances in a single subnet. There's no ARC broadcast domain. You're not going to have any of those limitations in VPC. So I always advise, consider large mixed-use subnets. Don't use them as isolation containers. Make sure you have a very large, diverse ability to pull from IPs. And you're not constraining one subnet because this is the subnet for app A, and you run out of IPs over there, but you can't pull IPs from another subnet because that subnet's for application B. It's not necessary in VPC. Use security groups instead to enforce isolation. By default, you get to start with 500 security groups in a VPC. That's much more robust ability to isolate things than subnets. And then tags for grouping resources. Tags can drive cost allocation. They can drive very fine-grained permissions and controls through identity and access management, or IAM. You can't get that out of subnets. So what do you use subnets for? You use subnets as containers for routing policy. That's really what my primary recommendation is. Think of them as containers for routing policy, and we'll talk about what that means. And if you don't know what I mean about when I say performance and thousands of instances in a single subnet and why that doesn't matter with VPC, please go watch this talk. Net 401 will give you a really good under-the-hood perspective of how VPC really works. So here's a good starter home. This will work for 80% of you for both starting and a long way into the future. Have many very large and complicated customers using a very similar subnet design in a single VPC. And those of you that you can see here, /22 give you 1,000 in your public, a little over 1,000, and the /20 will give you a little over 4,000. Just this distribution means you have about 50,000 IPs still left over for future expansion. So it's a good start. But we're actually going to start with 3 subnets per AZ because I do want to focus on that point about routing policy. So I have 3 different routing policies for this VPC. So a subnet dedicated to each one of those routing policies, and we'll go through what that means. So I took my advice and I put a /16 on this VPC. The first routing policy, the first is to point out that by default, all the subnets in a VPC can talk to each other. So it's a flat network. It's a star. There's like a virtual router that is represented in each subnet by this .1 address, which is handed out by the VPC DHCP server. And that every route table, by default, will have this local route that facilitates that routing within the subnets. That route is put there by default, and you cannot manipulate it. So the first of my subnet policies is I'm going to have a public subnet. So anything I deploy in this public subnet is automatically going to get a public IP. I'm going to create an internet gateway, an IGW. This is a logical construct that allows and facilitates the egress and ingress of traffic into the VPC. So just attaching the IGW doesn't mean that automatically you've opened up your VPC to public traffic. It just gives the facilitation of that. What you also have to do is provide a route to the IGW, which you see there. So your default route now is pointing to the IGW. And with that and public IPs, instances in that subnet can now egress out the internet gateway and out to public networks. And depending upon their security group and network ACL configuration, they can also be reached from the outside. Now, my routing policy for my bottom subnet is very different. I want that bottom subnet to only be private IPs, no public IPs, and no routes to public networks. So it's going to be tied into my corporate network later. So I'm going to create a virtual private gateway, a VGW, you see represented there at the bottom. And that's going to be a termination point later for things like VPN tunnels or direct connect connections. And so you see there, I have added a route from my corporate CIDR block that represents my corporate network, and that is directed towards this virtual private gateway. So everything private is now directed there to reach those external networks. And then my third routing policy is this subnet in the middle, which is kind of a hybrid. So it's also a private subnet, so everything in there has private IPs, but we also want to facilitate those instances and resources in the subnets to be able to reach public networks. So how do you do that? Well, the first question is, why would you do that? Why would you want that? Why would you want private resources to reach outside? And there's a lot of reasons, and some of them might not be as obvious as others. The first one is AWS API endpoints. So if you're making any API calls from instances in these subnets, whether that's auto-scaling calls or moving ENIs or trying to reach AWS public services like S3 or Kinesis, Lambda, SNS, those are all public regional resources that exist on the public network. So you have to be able to get out of the VPC to be able to talk to those endpoints. And same with third-party services, any software platforms or PaaS or SaaS platforms that you might use obviously exist outside your VPC. So the traditional way to do this is to deploy a NAT instance. So this is an EC2 instance that's providing network address translation. So it has a public IP and fronts those instances that are only private IPs, translates, and allows them to egress out. And you facilitate that in the routing table by pointing your route to the actual NAT instance itself, the instance itself, to be able to get out. The problem with that is scaling, is that as your traffic increases and your requirements to get out through this NAT instance, it's a single point of failure. It has a dedicated amount of bandwidth. So it's not scaling. It's a single EC2 instance, and eventually you're gonna burn the thing up. So how do we do scalable and available NAT? So this is a first set of requirements. We're going to go through a number of these requirements as we go through our different designs. So this is the first one, where public subnets for resources are reachable from the internet. We have private subnets with egress-only access to public networks. We want scalable, available NAT, and for now we're dealing with just one AWS account, one region, and one VPC. So back to the NAT on fire. We used to have all these complicated ways to deploy multiple NAT instances, adjust route tables to go between them, and facilitate some kind of high availability with EC2-based NAT instances. Fortunately, late last year, we launched the NAT Gateway, which is pretty much from an object's perspective, a drop-in replacement for the NAT instance. You point your routes to it the same. It takes an EIP, elastic IP, a public IP address. So from the design perspective, it looks like a NAT instance. But underneath the hood, there's a lot more going on here that makes the NAT Gateway special. I'd like to just point out a few things. So why would you use a NAT Gateway over a NAT instance? Most of us know how NAT works. Private comes in with a source IP import. The NAT instance source NATs that. So it replaces that source IP with its own public IP. That's all well and good. The tricky part is that source port, because that has to be unique when you're talking to networks out. So if you have, for example, lots of instances going out and trying to get a security update that has the same endpoint out there, the same destination port and IP address, your source port has to be unique. It has to be unique connection for every single one. So as you have more and more and more connections going out to the same destinations, every time you're opening a new connection on the NAT instance, it's having to check its table, choose a new unique source port, and in a very atomic and transactional way, open that connection and make sure that that source port is unique. This is quite a a similar problem with a database, but databases work in milliseconds. This needs to work in microseconds. So the traditional scaling for a NAT instance has been to vertically scale it. Keep everything in memory, keep it fast, keep everything in microseconds. But horizontal scaling of NAT instances has been very difficult. And so that's where NAT Gateway comes in. We applied some very innovative engineering to address this problem of horizontal scale for NAT. So NAT Gateway is a fully horizontally scaled, has full replication of connection state, and is highly available. So there we are. We drop in the NAT Gateway. And there are a few requirements. It's not like an IGW or VGW where it's a VPC-wide service. You deploy a NAT Gateway in a specific availability zone. It's highly available and fault tolerant for that availability zone. So you still need that internet gateway. You still need separate subnets to be able to define the routing policy to use that NAT Gateway. It requires an elastic IP assigned to it, so it has a public address. And it's, each NAT gateway is burstable to 10 gig of bandwidth today. So it actually appears as an elastic network interface in your subnet when you create this NAT gateway. But you'll notice there's no security group assigned to it. It's because you can't assign a security group to a NAT gateway. So how do you secure access if you want to be very restrictive about who can actually use the NAT gateway? How would you do that? So the first thing is network ACLs, they still apply. So if you're doing some coarse grain control on the subnet access itself, those will still apply to get to the NAT gateway. The second thing is what I've been harping on, is use routing policy. So have subnets like we have that have a route table assigned to them that allows them to use the NAT gateway versus subnets that don't. And the third one is really the key one. So use security groups to restrict outbound. So I find most customers don't ever mess with their outbound rules on their security groups. And by default, if you create a new security group, your outbound is open to all traffic. So you see there, a destination for everything, port range for everything. That's the default VPC security group. So what I recommend is having dedicated, so your default, change it. Make it only RFC 1918 space. Make it only the space within your VPC. If you're doing a lot of other network connectivity, other networks and stuff, this might look a little different. But the default here is I put my outbound only to my VPC side only. So they can only talk to stuff in the VPC. And then I create a separate NAT-enabled VPC security group that then enables them to go anywhere. So that gives, the default now is much more locked down. So you can do this. You can have one NAT gateway and multiple AZs using that NAT gateway. But as I said before, it's an AZ-specific deployment. So for real availability, if something ever happened in that AZ, you would have lost all possible NAT functionality in your VPC. So we always recommend to deploy one NAT gateway per AZ. Oop, sorry. You'll get the slides later. Too fast to take the picture. So pros and cons of NAT gateway. So pros, it's a drop-in replacement for NAT gateway. For NAT instances, it's very easy to migrate. You just update your route table. You can even migrate the EIP over if you want to be consistent. The only caveat is that obviously you're going to lose any open connections that are open at the time that you do the cutover. It's fully managed, it's highly available and fault tolerant, scalable at 10 gig, and it supports VPC flow logs, so you can monitor and track all of the network traffic that's going through the gateway. On the con side, there's no higher level functions. It just does NAT. So those of you that are deploying NAT instances that are doing things like IPS or UTM or any kind of URL filtering or packet inspection, more of the high level security functions, that's not the NAT gateway. So we have lots of partners that offer those features in their NAT instances along with providing NAT. So whether that's our Sophos or Fortinet, or we have a whole range of partners that provide security appliances that do these high-level functions. And as I mentioned, you can't associate security group. So here we are. We have our one VPC, and now we're moving on to our next one, where we have an internal-only corporate IT app that we want to connect to our internal corporate network over IPsec tunnels. So what are the considerations when we're talking about multiple VPCs when you start moving into 1, 2, 3, 10, 100 VPCs? What should you be thinking about, and why would you want to do that? And why not one big VPC? And my first question back to you, whenever I'm asked that from a customer, is, well, why not one AWS account? Because those two go hand in hand. As soon as you have more than one account, you have more than one VPC. So there are a few things that go with both having multiple accounts and multiple VPCs. And the first one is blast radius. So if you have one VPC and you have thousands of developers, somebody's going to step on each other's toes. You know, IAM allows you to give very fine-grained resource control over who can do what in your VPC, but you cannot IAM API limits, right? So if, for example, you have one misbehaving app that browns out your throttling limits on EC2 describe calls, that affects everyone else. So there is a certain level of blast radius that you must consider when you're putting resources in a VPC. Oh, this thing is going to drive me crazy. Here's another very good reason to have both multiple accounts and multiple VPCs. It's probably the best reason out there. If you're not doing that, come talk to me. Same with this one. You know, regulatory and compliance reasons, keep them as separate accounts, separate resources. This is also another very common one. So with disaster recovery, separate region and separate account. So you have all of your data replicated to a different region for disaster recovery. And in case there's some kind of compromise in your account, in your production, that compromise cannot affect your disaster recovery because it's all in a separate account, separate VPC, completely isolated. And then we do some things a little fancier to illustrate, you know, where we go with more VPCs and more accounts. So here we have, you know, an account and a VPC per business unit. And we're sending all the application logs, S3 access logs, ELB logs out of these accounts and these VPCs from these business units. You know, they're able to manage their own bottom line, have cost visibility, and get their own bill because they have their own account. But we're sending all of their, you know, digital exhaust to a separate account. You know, things like AWS config also to track all the changes within their VPCs. So if somebody changes a security group or changes an internet gateway, alters a route table, you're going to know about it. CloudTrail to monitor all of their API calls, you know, the audit log of all their API calls. And then VPC flow logs, again, so that you know all the traffic that's going in and out of their VPCs. All this stuff is going to another account and another VPC dedicated to logging, to auditing, and analysis of this data. So you might have EMR in there doing you know, MapReduce jobs to reduce this data. You might have Amazon Redshift doing, you know, data warehousing of this data for querying and analytics. And then, of course, S3 as the storage backend. So now we've gone through some of the reasons why you would consider multiple VPCs. Let's dive back into our private app. So this is the one we showed before, where we have only a private connection to a corporate network over an IPsec tunnel. But the application in there wants to make heavy use of S3 as a primary data store. So how do we facilitate, in a private-only VPC, access to a public resource like S3? So our next round of design requirements. So VPN connectivity to private-only VPC. No egress in the VPC to public networks. So no public IPs whatsoever. Private IP access to Amazon S3. Very content-specific egress control, access control, so we control exactly what goes out of the VPC, and be able to filter it. And one AWS account, one VPC, one region still. So by default, if you didn't do anything else, this is the route that you would take to facilitate that connectivity. You know, you have to go down in your data center, all the way out your data center's public border, back around to the region. And that's obviously, it's not an ideal way to go. Fortunately, we have VPC endpoints, which are, there we go, to meet exactly this requirement, to provide private IP connectivity to AWS services, in this case, S3. So VPC endpoints, there's no internet gateway required. There's no NAT. You're not using public IPs. It's free, and you have very robust access control, and it's private IP connectivity to S3. So here's an example of creating an S3 endpoint and assigning it to a subnet. So this is the CLI. You'll notice you actually tell it what route table you want. So there we are, and it creates the route for you. So you see the destination is a prefix list, and the target is the endpoint itself. And we'll talk a little bit in a minute about what a prefix list is. And to give an example, here's a subnet that does have an internet gateway. What would happen if you created and assigned a VPC endpoint to this one? Here you have your default route is the internet gateway, but you're still using the prefix list for S3, for the service to access S3. That's obviously a more specific route for S3, so that's going to be used over the internet gateway for S3 in that region. If you accessed S3 in another region, that endpoint is only for this region, in this case, US West 2. So you would use the internet gateway to go to another region to access S3. And what if you had a NAT gateway? So if you already had a default route out of the NAT gateway, it's actually really important that you also add the VPC endpoint to that private subnet, because otherwise you're funneling all of your S3 traffic through the NAT gateway. And if you know the NAT gateway, it's charged on the data transfer rates through that NAT gateway. So the VPC endpoint is not, it's private IP. So it's a cost decision there to add a VPC endpoint to subnets that are using NAT to get out of the VPC. So prefix lists are an abstraction. So they basically represent the entire public IP space of S3 in the region. And so all you need to do is reference the prefix list, and it will figure out what the actual backend IP is. And this solved a lot of headaches that customers had before in trying to keep track of what actually consisted of S3 IP space. So obviously those ranges change all the time in the back end, but all you have to do is reference the prefix list. And you can use them in your outbound security group rules. So similarly to how I advised with the NAT gateway, you can do the same thing to restrict access to the VPC endpoint. So you can say only certain instances in the subnet, even though the subnet itself has a route to the VPC endpoint, you can apply a security group to instances to restrict them outbound to be able to use the VPC endpoint by referencing the prefix list. And here's the fine-grained access control I mentioned. So there's multiple stages you can be able to apply policies to control egress out of your VPC. So the first one is I can apply an IAM policy to the VPC endpoint itself that says it can be as detailed as users and groups, amount of content, specific objects. In this case, I've gone pretty generic, which is a specific bucket. So you can only use this VPC endpoint to go out to a specific bucket. So I apply it to the endpoint, and it's only for get and put. And so instances that are in that route, that have the route to the VPC endpoint are allowed to get out if they are going to that bucket. So that's on the endpoint itself, but I can also apply a policy on the bucket. So you have it on both ends. Now the bucket can say only specific VPC endpoints or only specific VPCs can talk to me. So here we check and make sure that it's coming from a very specific VPC endpoint, and if it is, then you're allowed access to the bucket. So multiple stages of access control. So just to recap real quick. So you have the route table that gives the subnet, the resources in the subnet itself. Again, subnet defines routing policy, gives access to the VPC endpoint. The second is the policy on the endpoint itself that says what can go out of this VPC through this endpoint to access what resources in S3. The third thing is the bucket policy itself, which says who can access this. And then the fourth is the security groups. So multiple stages. So we'll just give a little endpoints in action here. So we create a backups bucket for all these internet apps so that they can push those up to S3. But we have a compliance application which has more fine-grained requirements around what can go out. And so we create a separate endpoint for them. So you can create multiple endpoints and have different policies on these endpoints on a VPC. The restriction is that you can only have in a route table one route to S3, so that prefix list. You can't have multiple ones. So for example, if I wanted to add more buckets, I wouldn't be creating new endpoints for these subnets because they already have a route to an endpoint. So instead, I would have to alter the policy itself to allow access to these additional buckets. So pros and cons of the endpoints. So secure, highly scalable, highly available, access to S3. You don't have to worry about scaling it or bandwidth. Fine-grained control of access to the content in S3 from the VPC. You can control which VPCs, which endpoints can access which buckets. And there's no public IPs required. It's all source IPs accessing S3 are kept private, your private IPs from your VPC. Negatives, so cons. If you do restrict an S3 bucket to a specific VPC or a specific VPC endpoint, you can't use the S3 console anymore to manage S3. I hope that's obvious why. But the console doesn't run in your VPC. So as soon as you put that policy out there, you will go into the AWS management console and you'll get a nice big error. And you need to enable DNS. That doesn't mean you can't use your own DNS. If you do, you just need to forward it on to the Amazon EC2 VPC DNS, because we've got to resolve those prefix lists. All right, so we got 2 down. What's next? So this is the part where this usually happens. You know, the easy deployment methodology of VPCs, the ability to spin them up very fast, do projects, do tests, and then actually deploy applications and connect them back into your corporate networks, you're going to have a lot of VPCs very fast. And while that dynamic nature of VPCs is a great feature, you know, adding IPsec tunnels, bringing in new networks, propagating those into your corporate network, making change control in your network border, these are impactful changes. And when they're coming rapid fire like this, your network engineers are not going to be happy with you. So to emphasize, you know, just what's involved in just one of these VPN connections, let's zoom in on one of these and see what is a real HAVPN to VPC connectivity looks like. So every time you create a VPN connection to a VPC, it's 2 tunnels. So that's the redundancy on our end. So one tunnel will land in separate availability zones, and that will connect down to one of your customer gateways. So this is your VPN device terminating the tunnels on your end. Now, to provide HA on your end, you're going to want 2 customer gateways. Come on. So that you can have redundancy on your end. So now we've got 4 tunnels. So 4 tunnels are involved in each connection. And then BGP, please don't do static routes. Always dynamic, always BGP. And this is the arrangement when you connect to us. We advertise down our ASN and the CIDR block that comprises the VPC itself. You advertise up your network, so your internal corporate network. What also comes down from us, if this will work, are MEDs. So multi-exit discriminators. So this is a way for BGP for us to influence the routes that come down to you. So we use those in our VPN as a service that backs the VGW to tell you which tunnel we're going to prefer. So you need to make sure and honor those when they come down. And you can do the same to us. So if you want if you want your traffic to prefer one CGW over the other, you can do the same. You can send up to us either MEDs, or you can send up AS path prepending to favor one side or the other. And then obviously you would re-advertise the VPC CIDRs that you're learning from the VPC into your internal network through whatever IGP protocol you might be using on your corporate network. All right. So we're starting to stress out your network pipes. We're starting to really stress out your network operations team. And all these things are accessing common shared services that exist on your corporate network. So whether that's DNS or directory services, logging, monitoring, security, common data sources, all of that's coming down. So our next set of requirements is to fix this situation. So how do we centralize network connectivity so we're not being so impactful to our network teams? Centralize the management, security, and the common service access. Give account owners some kind of control and freedom over their own VPC resources, but still have centralized security control over that access. And now we're moving into many AWS accounts, many VPCs, still one region. So this model is a hub and spoke with peering. So we are going to facilitate this by moving those common shared services up into a hub VPC. So this shared services VPC that you see here. And then all of the spoke VPCs will be peered through VPC peering. So this is a one-to-one relationship between a spoke and the hub that facilitates private connectivity between VPCs. And you'll notice the shared services VPC is the only one that has a consolidated connection down to your corporate network. And it's also the only one that has any egress to the public network, so the IGW and the VPC endpoint. They're all only in the shared services VPCs. The spokes are completely isolated. So let's zoom in on the shared services hub and one of the spokes to see how it works. So here we see the establishment of the peering connection itself. So this is an API call where both sides have to agree. So you send it to each other and you both thumbs up. That facilitates the creation of a peering connection. That doesn't mean everything can start talking to each other all of a sudden. What it does mean is you can now start creating routing rules that reference the peering connection. So you'll see here I create a private route table on the spoke that says I want to reference the shared services subnet through the peering connection. You can be as specific as you want. You don't have to say the entire VPC through the route. So you can take this down to a /32, and that means that your spoke would only be able to talk to a single host over that peering connection. But on the other end, we give the shared services VPC access to the entire VPC space of the spoke. So now these two can actually route between each other, all private IP connectivity between the two VPCs. But what about if I want to reach down from the spoke into my corporate network? I can add a route for that. So I've done that here to reference the peering connection because that's the direction of my corporate network. But when I actually try to do that, the hub VPC is going to see traffic trying to egress that's not part of its network, and it's going to drop it. And that's by design. So you can't have a transitive relationship with VPC peering. So I can't be peered with something and then reach other things that VPC is connected to, whether that's exterior networks or other spoke VPCs or the VGW or the IGW or the VPC endpoint. All of those are transitive relationships. All I can do with a peering connection is talk to the actual CIDR space in that VPC that I'm peered with. But what if we do want to facilitate that kind of connectivity? What are our options there? So probably the most common initial is to deploy a centralized proxy. So a lot of customers, they already have centralized proxies for a lot of their outbound access, and they'll deploy a centralized proxy layer up into their shared services VPC, and will provide HTTPS connectivity to facilitate this end-to-end kind of communication. So how would that work? So here we have internal ELB deployed into the shared services VPC, backed by a proxy fleet. And this is not a transparent proxy. So this is not inline. This would be an explicit proxy. So you would have to actually configure your endpoints, your instances or devices, to use the proxy for HTTP communication. So here you see it going across the peering connection to the ELB, and hitting a resource in that VPC that can now use the VGW and down to your corporate network. And similarly, to use egress out of the internet. And this proxy can be a centralized source of URL filtering and determining what content can and can not go out. So it's a centralized resource for all HTTPS traffic. And you see here the proxy is the only one that has all the routes to all these resources. So let's zoom in and see like how this is actually configured. And you'll see here that I'm building up layers, but keep in mind that star network. So by default, everything is flat. Everything can talk to each other. So all of these layers that I'm representing are determined on security groups, routing policy, and network ACLs to actually form these layers. So first, we've got an internal ELB. So it's all private IPs. And that's the destination for my proxy. Backing it is the actual instances that are performing the proxying functions. So these can be, whether it's open source Squid or a third-party vendor that you're using to do your proxying. Those are behind the ELB. And they are the only ones that have public IPs, and they are the only ones that have a route to the Internet Gateway. And so the private subnet in the spoke VPCs, you can actually use security groups across peers now. So that actually wasn't possible until this year, is to share security groups across a peer relationship. So the ELB itself could have a security group of a spoke to say, these spoke resources can use me and are able to access the ELB. And similarly for accessing public resources, how we go. Same for using the VPC endpoint. And finally, administrating it, so operations staff back on your corporate network, they're going to have to land on something in that shared services VPC, so something like a bastion host, administrative host, that they land on that they can then jump on to spokes or any peered relationship. But they can also use the proxy. So if you want to facilitate, for example, S3 connectivity, private S3 connectivity through your VPCs, through the shared services VPC, you can certainly do that. And so those devices can be configured to use the proxy in your shared services, and out they go. So a few to-dos on the shared services hub. Make sure you're using IAM to control. I talked about these teams owning their own VPC, having their own account, but you got to make sure that they can't alter the design that you've put in place. So you got to make sure they can't tear down the peering relationship or put an IGW on their VPC. So all of the high blast radius network-specific API calls, you need to make sure you're locking those down. So create NetOps roles and make sure you apply these roles to every one of your accounts so that your network operations teams are the only ones that can jump in there, assume that role, and make network-related VPC changes. There's a link there for, we now have managed roles. So there's one for network administrators, which means it's a managed policy, which means AWS is responsible for keeping it updated. So as we release new network-related features and products, that policy will automatically be updated. So take a look at that. We've talked about CloudTrail config and VPC flow logs. Make sure you're making use of those to track everything that's going on in all your VPCs. So quick pro-con on this one. So we're minimizing on-premises network changes by consolidating down to a fixed number of pipes up into the region. We've reduced latency and the cost of cloud applications because we've moved those shared services up. They're no longer having to come down to your corporate network to access them all. We've provided spoke accounts control over their own resources, but we have centralized control of everything that's coming out of them with the proxy. And the security groups are working across all the peers so that we're securing the traffic. On the con side for the hub and spoke, obviously you're managing the cost and the management of the actual proxy. So all those instances that comprise the actual proxy are your responsibility. I mentioned it's not a transparent proxy, so you're having to do the configuration to point everything to that proxy to use it for HTTPS. It's restricted to L7, to HTTPS. And we point out the no transitive networking and the peering data transfer cost. So there is a cost to use peering, 1 cent a gig. And so if you're doing very significant data transfers between peered VPCs, you want to pay attention to that traffic and figure out whether the peering makes sense for you. All right, so here we got multiple hubs. You know, you have maybe a dev hub and maybe you have a prod hub, but it's not limited to just that. You might have a data services hub that might be tied in, but they can be connected to each other. You know, peering is very flexible and it can also be dynamic. So it's something that I don't think is quite apparent at first blush with peering, but you can have, you know, it's just an API call to establish connectivity between two VPCs. So you might have a deployment use case where you have a promotion of data from one environment to another. And traditionally, these environments wouldn't be connected. But programmatically, you could just issue a VPC peering connection, connect them up, transfer the data, tear down the connection. But now we've got your next hot mobile app in one of these spokes. So we're going to zoom in on this one spoke in the hub. So we have this mobile app. And this is what I'm calling a hybrid serverless, which I'm trademarking. And this is, I'm seeing this more and more, where you have a private VPC. The resources in there have no IGW. They're all private. But you're using public AWS resources to provide a front into the resources in the VPC. So for example, Amazon API Gateway is providing a landing point for your mobile APIs. And it's providing strong authentication, and it's providing metering, and it also provides access to Lambda functions. Lambda can reach inside your VPC. So Lambda can privately access your VPC. It does that by creating an elastic network interface that the function then uses to access. You know, the interface itself has a private IP from your VPC, and it uses that to access resources in your VPC privately. So there's no public access here. So here we're accessing, you know, we have a backing store of Amazon Aurora deployed into this VPC for the mobile app to use, and that works great. But what doesn't work is the new functionality that we want to launch, which depends upon legacy applications that are still back in your data center back home. So this is very common where customers are, you know, advancing their mobile application at a certain pace, releasing new features, but they have dependency on the legacy applications. They can do this, build these things up in the cloud, and still be able to reach back to legacy apps and make use of the data that's still on your corporate network. How do you do this? You know, we've already talked about transitive not working. So here we go. We got all these spokes now that have requirements to have end-to-end layer 3 connectivity. So no longer just proxy, high-level layer 7. We want end-to-end connectivity. And we've also got some other regions out there that are growing. We'd like to bring them into the fold. So now we move on to VPC mass transit. So here's our requirements now. So now we want to, again, we're centralizing and minimizing the network connections. But now we want to allow end-to-end routing. Minimal operational overhead, and we want to leverage the AWS network with many AWS accounts, many VPCs, and many regions. So this is where we're going to bring in the concept of a transit VPC. And a transit VPC is dedicated to just that, facilitating connectivity between networks. So we keep it as simple as possible. All that's going in here are dedicated EC2-based routing devices that are going to be responsible for maintaining VPN tunnels to a lot of different networks and facilitating the communication between all of them. There's no other resources in the transit VPC. We keep it simple, just has a default route to an IGW, and no other resources in the VPC that are depending upon pointing to these things. And then we start adding spokes to them, and the spokes are dead simple. They're just pointing a default route out to their VGW. It's kind of turning the model on your head because, you know, these EC2-based VPN devices are basically acting as customer gateways. But in this model, it's the reverse. They're not really the client. They're the hub. So as we add more and more spokes, and this is, again, all BGP, all dynamic routing, we're learning all these networks, and these centralized transit routers are facilitating end-to-end connectivity between all the spokes. And we can do the same for bringing in external networks. We just land the VPN tunnels and connect them directly to these transit routers. And it's, as I mentioned in the proxy, these are now centralized methods for traffic control, for security and filtering. So if this sounds like something you're actually interested in, the Solution Builder team at AWS has actually built a solution for Transit VPC, and we're going to talk a little bit about how that works. So there's a CloudFormation template that sets all of this up for you. It's based off the Cisco Cloud Services Router, so the CSR, which is a full stack virtualized ASR. So it has all the features of your hardware ASR, but with a BYOL, a pay-as-you-go license model. And the CloudFormation stack for Transit VPC, launch it. And in the template, all you have to do is choose what bandwidth you want. So at the low end is 2 with 500 megabits, per router, all the way up to 4.5 gigabits per second per router. So it creates that Transit VPC for you, deploys them with EIPs, assigns carrier network space to it. So this is not RFC 1918 space, it's shared access space. And then it has a very cool automation to be able to actually start creating your transit connections, so spoke connections. You see, very simple. All we have is the IGW route, and it uses S3 for storing configuration, so we have a route to a VPC endpoint. And how do we do availability for these things? So I'm sure you're wondering, like, obviously you have centralized routers that are now responsible for all this communication between all these spokes. We use EC2 auto recovery. So if you're not familiar with this feature, this is all driven by a status check alarm called status check failed system. So this is a CloudWatch metric that is a summation of a bunch of EC2 related health checks that are rolled up into this one single metric that say what the health of the underlying host, its power, its networking, its software, everything about that physical host hosting your instance. And what you can do is set, when the alarm is triggered on that metric, if it fails, you can trigger to recover the instance, which means it will be migrated to new hardware automatically, and it will retain all the characteristics of that instance, from private IPs to the ENIs that are on there, to the EBS volumes that were mounted, all the way to the instance ID itself. So it is identical. And this is supported on all the instance types you see there. With EBS only, it's dependent upon EBS storage to facilitate the migration. So how do you add a spoke? So this is all driven by tagging. So you go to the VGW of the spoke. You add this tag that says transit VPC spoke equals true. There's a Lambda function out there that's running every minute that cycles through all of your accounts and all your regions to check for this tag on a VPC that does not have VPN connections already. So it finds that tag. It builds the necessary VPN connections. So it creates the CGWs if it needs to, the customer gateways, creates the VPN connection. It bundles that up into XML file and encrypts that and stores that on S3, which triggers another Lambda function by putting that object onto S3, launches a Cisco configuration, takes that configuration, puts it into something Cisco-friendly, and then actually uses the same private access, Lambda access, so it creates an ENI, has permissions to SSH into your transit routers, and pushes that configuration into the CSRs automatically. So within a matter of minutes, those networks are connected, the tunnels come up, BGP shared, everybody's happy. And you can also use, there's some knobs and dials in there to be able to do route influencing. So if you want a preferred route between your CSRs, you can do that too. So by default, they're active-active, which is fine if you're stateless. But if you're doing something like if these CSRs are also going to do NAT, or if they're going to do stateful firewalling, or anything that needs to maintain state and not have asymmetric routing, then you'll want to look into this feature. So this, again, just representing all the tunnels here, is driven by a tag that you put on the VGW. So you put a tag that says preferred path equals CSR1 or CSR2. And that will, again, drive a configuration change to prefer one or the other. And I promise this is my only router configuration screenshot. I just wanted to show you that this is what it does. It just automatically adds a path prepending in there to influence that route. So this was from the CSR2, which is the one you didn't want to prefer. So it doubles up on the buffer. So that is going to be obviously less preferred. And it applies that route map to that neighbor. Oh, I think it's finally dying. And the same is for removing spokes. So all you have to do is change that tag, either false or blank it out or whatever. That poller is going to be running every minute and checking the state of that tag, and it will tear down that connection, push the new configuration that has removed those connections. Cisco configurator Lambda function will launch, and it will reconfigure your routers for you automatically. So it's fun stuff. It's, I encourage you to check it out. It's fun to play with. It's really easy to launch the template and get running and start figuring out if it's going to work for your multi-VPC configuration. All right, so here we go. It looks very similar to the hub and spoke, but now it's all L3. So this is all driven by tunneling, IPsec tunnels into these centralized routers, and BGP driving all the dynamic routing between all of the various networks. So you can go everywhere. You can go from your branch to a spoke. You can go from a spoke to another spoke. You can go spoke to the internet. So full end-to-end. So now we're starting to get there. So we're bringing in that second region also into our transit. We're representing here that you can run a transit hub in each region, or you can move other regions over and have spokes. You know, it's completely up to you how you want to run the transit VPC. And you know where you want your point of consolidation to be. And I just point out here that we're also running full mesh between transit hubs, 2 different regions over the AWS network. So real quick, pros and cons of the transit VPC. So end-to-end routing, central transit routers can perform higher level functions. They're a central point of control for you. The spoke VGWs are dead simple, and they're HA by default. This minimizes on-premise networking changes because you're not changing anything about your connectivity to the transit VPC. All the really dynamic stuff, you're launching all these new VPCs, that's all happening in the transit VPC itself. And it can minimize cost if you're already doing this, and you can offload this function from purchasing new networking gear or something for a colo. Instead, you can move this up into a transit VPC. On the con side, we see availability and management of the transit router is up to you. We talked a little bit about the availability, the licensing cost of Cisco, and the cost of the data transfer is important to point out because everything transit related is going over the IGW. So it's all internet out. So for example, if you're going from transit to spoke or spoke to transit to home, each one of those is an internet out step. So you need to pay attention to your data transfer costs. So if everyone's okay, I'm running low on time. I didn't realize how this was going to go. I've got one more section, take about 5 minutes, but I'll try to blow through it. So this is just bringing in direct connect to this picture. And more regions. So we want to use an existing private network that we have. So we have an MPLS network. We don't want to use the internet anymore to connect our regions. We want to take advantage of this pre-existing network. And we want to bring in more regions. So dedicated scalable network connectivity to AWS, leverage our existing corporate network, predictable latency, and many regions, many accounts, many VPCs. So transit VPC with Direct Connect, this works perfectly fine. And there's actually a cool little feature here with what we're calling a detached VGW. And for those of you that are the VPC hackers in the crowd, you will noodle on this one tonight to figure out what else you can do to play with this one. So this is a cool one. You can use a VGW without actually being attached to a VPC. I don't know if you ever tried that, but you can. So if I tag this thing with the transit tag, the transit router is going to build up tunnels to this VGW. Now, right now, it's one-sided. There's nothing else attached to the VGW. But you can attach a private Direct Connect interface to it. So now, on one side, you've got the private virtual interface for Direct Connect attached to this VGW. On the other side, you have your VPN tunnels into your CSRs. So all the BGP propagation is going to happen and facilitate through this like free-floating life raft of network connectivity that's not attached to a VPC. So this scales up to about a gigabit of flow. So if you're doing multiple gigabits, you can create more of these. But if you're doing like 10s and 20s, 30, 40 gigabits of traffic over Direct Connect, you don't want to do this. You want to go a more traditional route, which is setting up the private Direct Connect directly into the VGW attached to the transit VPC, and then running tunnels over Direct Connect. So you can do this privately, like this. So here we're representing the tunnels from your on-premise VPN devices directly into the CSR transit routers. Or you can also do it over public. It's up to you. There's pluses and minuses on both. So with public, it's a public network now. And you're getting all of AWS public IP space advertised down to you. And you also have to secure that on your side. You have to treat it like a public network. So you'll have firewalls and such. There we go. NAT security layers on your side, because it is a public network. But you can still facilitate the tunnels across the Direct Connect connection. It's private, dedicated bandwidth. And you'll just be terminating those tunnels on the public EIPs of the transit routers instead of the private IPs. The advantage of the public is that in the US, once you connect in one Direct Connect location with a public Direct Connect interface, you get access to all the AWS regions. So if you were running transit hubs in multiple regions through this single connection, and here we represent it in the Equinix in Chicago, to the new US East region, is where you're directly direct connected into. So you obviously have access to your regions, all your VPCs in that region, but you would also have access to the remote regions if this clicker would ever work. So you'd be able to VPN and it would still be all over AWS private network. You would not be able to do that with a private Direct Connect VIF. Private Direct Connect interfaces can only be connected to VPCs in the same region that you're direct connected into. I'll skip this. This is going to be homework for you later. There's a really good deep dive if you want to go to all the details of Direct Connect and VPNs, NAT 402. And just real quickly, hooking up an existing MPLS, like IPVPN network to a region is dead simple. Most of your providers, they're already in our Direct Connect locations. That AWS region is already a point of presence on their global cloud. So all it is facilitating adding that new POP to your existing IPVPN, calling up your provider and saying, hey, I want to add US West 2. I want to add to the network. Because they're facilitating all the routing. You're having that relationship with their PE routers in each of your locations, and they just bring in that new network onto your VRF representing your cloud, and now you've got all of the CIDR blocks from the AWS region. So same with bringing in multiple locations. Here we have Chicago and London. The only thing to watch out for is as your MPLS cloud gets to a certain size, there are some limits. So there is a 100 route max in the VPC route table. So if you have many points of presence on your MPLS cloud, you're going to need to get your provider to either summarize those down to nice and clean smaller routes, or advertise a default route to you, because 100 is a hard limit for us in the VPC route table. And then you're obviously going to be seeing our ASN coming in from different locations, so you're going to have to do things like BGP AS override to make sure there's not any BGP loops when you're bringing in multiple regions. All right, so pros of using Direct Connect with Transit VPC: private network, no internet dependencies, predictable latencies because you have that dedicated bandwidth, those dedicated links into the regions, and access to public networks of all US regions over a single US-based direct connection. On the negative, you're getting all of our public IP space. You might not want all that, so you might be having to do some filtering on what you get from us as far as public network announcements. And then the 100 route limit we just talked about, and obviously the cost of a provider network and of all these direct connections. All right, so we finally got to the big picture. Thank you very much for your time. Sorry I ran a little bit over. I really appreciate it. Please give me feedback. Thank you.